let's look at the last try it yourself on the other page. And actually, we've already done this in our previous videos, so we're just going to skip this one. But it says, return to the example regarding the sound of a person's voice and whether or not that will help us to determine who is taller. The example we did a confidence interval for a couple videos ago. So, and what our final conclusion was, we were 99% confident that the true average of the percentage someone would score correctly was somewhere between 58 and 65% correct in terms of identifying who's taller just based on the sound of their voice. We could do the same sort of deal for a confidence interval. So let's look at number C, or letter C. It says, does the data give good reason to think that the mean number of correct identifications in the population is greater than 50%? And so, as I kind of discussed at the end of the first that previous video, yes, it does, because we're 99% certain that it's somewhere between 58 and 65%. But we could also do this in the form of a hypothesis test. Again, because those, as I said in class, hypothesis tests and confidence intervals, they're not really different. They're kind of just different logically, but the math at the end of the day is exactly the same. It's all about the interpretation. But if we were to write out H sub 0, the claim should always be a statement of equality about the population. And then the alternative hypothesis, what we're sort of looking at here, which would be that it's greater than 50%. And so what we can say is that our null hypothesis, that let's say that the mean is 50, meaning it's just a randomized chance that their score is they would have 50% correct. Again, that would just be random chance, right? If I had listened to the same voice every time, I would just guess who's taller. I would have no idea. But our alternative hypothesis will be that people can't actually tell the difference, that it is greater than 50. And if we were to perform a significance test, again, we could do all this math by hand. Our statistic would be x minus mu naught divided by s over root n. And again, using all the data we used previously, we used our calculator to obtain the sample mean and the sample standard deviation. We got 62.17 and 5.81. So 62.17. Again, in our null hypothesis, that there is no determination that the average will be 50. And then the standard deviation, I already forgot. We obtained 5.81. Oops. 5.81 divided by the square root of the sample size, which I believe was 24. And again, we could do our t-statistic, blah, 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 find it in the t-table, or we could just use a calculator. Let's just do that to save us a bit of trouble. So we have, again, a t-test. Our null hypothesis here is that we have a 50% chance at guessing the correct who is taller of the pair. And our sample mean was 62.17. This seems significant just without doing anything, but we got to run the numbers. Our standard deviation was 5.81, and our sample size was 24. And we were under the assumption that we had a greater probability in this particular case. Calculate, and what we end up with is a t-statistic of 10.26. I assume that is consistent with what we would have had if we would actually calculate it. And our p-value is, well, very, very, very small. So p-value that our calculator comes up with is, remember that, I don't know if I've mentioned this to you guys before, but in the calculator, if you ever see this e to the minus 10, if you're like, what does this mean? This is the calculator's way of doing scientific notation, or just one of the ways it represents it for some reason. But basically, it'll give you 2.34. What this means is multiplied by 10 to the minus 10 power. Or essentially, you need to move the decimal place 10 spaces to the left. So if I move it 10 spaces to the left, this would be 0.0000. It should be 9 zeros. 1, 2, 3, 4, 7, 8, 9, 2, 3, 4. Or essentially, this p-value is basically nothing. Very, very small, less than a percent of a percent of a percent of a percent. Or, again, this is super, super strong evidence. Basically, we are very confident in rejecting H null because p-value is significantly less than alpha over 0.2. So the short answer is yes, this is significant data. And I would conclude that the correct identifications of U.S. young adults is greater than 50%. Also, if we were to do this in a T-table, I wanted to mention a couple things about it that I think I forgot to before. But notice if we go to DF of 23, and we look for our T, like notice here we had a T statistic of 10.6 or 10.26. Notice that 10.26 is nowhere to be found, right? It would be significantly greater than even the last entry in the table. And all that means is that the probability is significantly smaller than these, right? Because it stops at 0.0005, but our probability was 0.00000002. But essentially, it doesn't go any smaller because, you know, anything higher than the table would be statistically significant because it's way smaller than even your standard alpha levels. And another thing that you were probably wondering is, what if I get a degree of freedom that's not on here? What if I get a degree of freedom of 43 or 200 or 700? But basically, just use the closest available option. So say your degree of freedom was 43, I would just use 40 and go from there. Notice that there's not a substantial difference between these degree of freedom values from 40 to 50 to 60. So you could always split the difference or try to approximate, but just use the closest one. It's going to be a little bit off, but again, these procedures are not perfect at the end of the day, and there's always a bit of error. And you know, say you had a 400 as your degree of freedoms, just use 100. It's close enough. Notice the difference between 100 and 1,000 is very, very small. And the last thing that I mentioned before is notice that Z star is on this table, and it seems a little strange to put your Z critical values here as well, but technically, if you have an infinite degree of freedom, that's equivalent mathematically to having a Z distribution, because a Z distribution is when we know the standard deviation of the population. But if you have a super, super large sample, basically you have a high degree of freedom, it will be the same thing. And that's why as the n gets greater, it will get closer and closer and closer to a normal distribution. And really, a T1000 distribution is virtually indistinguishable from a normal distribution.